Okay, good morning everyone. We're here for, as you can see, an introduction to Linux IPC by Michael Karisk. Michael Karisk, I hope I'm pronouncing that right.
You are.
Is the author of the highly praised book, The Linux Programming Interface, a guide and reference for system programming on Linux and Unix. Since 2004, he has been the maintainer of the Linux Man Pages project. Michael lives in Munich, Germany, and works as an editor and writer at lwn.net. Thank you very much for coming and talking to us today, Michael. Over to you.
Thank you. Good morning. There's quite a lot of you. That's good. Okay, I don't think I need to say much more about myself. That was a nice introduction. So I'm here to talk about Linux IPC. I've got a very limited amount of time. There's actually a lot of IPC, so I'm going to be reasonably quick, and my goal is really just to give you a flavour of the kinds of IPC there are on Linux, a few code examples, and some discriminating factors that you might use to choose between different IPC methods. IPC, inter-process communication. In case you didn't know, you might be in the wrong place. Okay. So I think that's all been said. I'm the Linux Man Pages maintainer. Was that mentioned? Yeah, I've been the Linux Man Pages maintainer for, it's coming up to 10 years soon. A lot of the diagrams you'll see do come from that book, which is nicely product placed there. I've got 2 copies. You can feel free to browse afterwards if you like. More information online if you want it. I'm going to assume that you can read a bit of C and that you have an idea about some basic system calls in Linux, Unix, fork, read, write, open. But you don't need much more than that to follow what I'm going to do today. So the first thing to know is there is a lot of IPC on Linux. I think it's nearly a complete list. It's as complete as I could make it anyway. So there's something like about 20 or so different things there. If you want to try and understand it, the first thing that helps to start with is to try and classify it. And that's a first attempt at classification, where I've divided mechanisms into communication, things that are about exchanging data, synchronization, which is about coordinating activities of processes, and signals, which don't quite fall into either category, but can be both. Of course, whoops, what's happening here? Oh, hang on a second. Sorry. Of course, you can use communication methods for synchronization. If you are tricky about it, you can even use synchronization methods to communicate data. So you can flip bits and semaphores backwards and forwards as a means of exchanging bits between 2 processes. It's just, why does this keep happening? Okay, something's wrong here, that just my slides are sliding forward and I'm not sure why. So if we try and break that taxonomy down a little bit further, there's a whole bunch of communication methods, which again I've tried to break down into categories. Broadly, 2 main categories: data transfer methods, which are about writing data from one process and reading it into another. So there's a transfer involved where user space sends the data to the kernel and then another process gets that data from the kernel. So there's 2 copies involved. You can divide those data transfer methods further into 2 main categories: byte stream and message. Byte stream, the data is just an unlimited sequence of bytes, and the reader can read as many bytes they like, regardless of how many bytes a writer wrote. Conversely, I think I'm going to just put that down. Conversely, you've got... Okay, let's go backwards.
Who's got a clicker in their pocket?
Okay. I'll take this out as well. Okay. So we had byte stream. The converse is message-oriented communication, where a writer writes a whole unit of data, and the reader reads exactly that unit. So there's no concept of partial reads or reading multiple messages at a time. A reader writes one message, a writer writes one message, a reader reads that message. In between, there's one other data transfer mechanism which I won't talk about much today, pseudo-terminals, which have a rather specialized use. They're not a general data communication technique. Now this is not something I set up. Who's an expert in LibreOffice? Where is Michael Meeks? Excuse me, folks, I'm sorry about this. Slideshow settings. Change slides.
Somebody should be Googling.
Okay, maybe we're going to have some joy now. So pseudo-terminals I won't say so much about. They're quite specialized as a method of data communication. The other general category of data communication methods is shared memory, and the concept there is that you've got a bunch of processes or a bunch of threads that are communicating by sharing some physical pages of memory, and the communication just consists of writing some data into that memory, then it's visible to everyone. Synchronization, again, there's a number of categories that you can divide things into. Semaphores, event file descriptors, which I might find a brief amount of time to talk about depending how we go today. File locks, again, which I might find a brief amount of time to talk about. Futexes, which I won't talk about because they're a very low-level mechanism. Futexes are used to implement semaphores or POSIX semaphores and some of the thread synchronization methods, and then there's a bunch of thread-related synchronization methods. Mutexes, condition variables, barriers, read-write locks, and I won't go into those today. So this is an indication we're going to try and cover today. The bold blue stars are the ones I want to try and spend some time on, and the pale blue stars are the ones I might get to if we have some time. And if I don't, you can always ask me questions later. Synchronization methods, mainly I want to talk about semaphores. We might find time to talk about file locks and event file descriptors as well. These are the pieces I'm not covering, and I think I've already explained in most cases why. So, communication techniques. The original communication technique on Linux was a pipe. Okay, a pipe which everyone's familiar with, where you have a command like alias, you have the pipe symbol, and you run it through to a command like WC to find out the number of files in your directory. A pipe is a byte stream, so a writer can write an arbitrary number of bytes in there, a reader can read those bytes in any size unit they like. Single bytes at a time, 2 bytes at a time, 100 bytes at a time, or so on. It's unidirectional, in other words, data only goes one way through the pipe. A pipe has a write end, that's the end that things go in, a read end where the data comes out. So a pipe is just a buffer in the kernel. You can't seek on it, you can just do sequential reads. And I said this already, it's reader, it's unidirectional. One thing, because it's a byte stream, you can't have multiple readers and writers. I mean, technically you can, but because data might be interspersed between writers, or readers would compete to read the bytes. Practically, it's difficult to do anything useful with multiple readers or multiple writers. So the way you create a pipe is with the pipe system call. What you do is you give it, oh, that's a typo there. That should say file, there's 2 there. You give it a 2-byte array of integers. Pass that as an argument to pipe. What it does is create this pipe, and the 2 array elements are the file descriptors that point to the write end of the pipe and the read end of the pipe. Easy to remember, 0 is for standard in, if you like, 1 is for standard out. It's the same convention, if you like, for those 2 array elements. And then you can just write into the pipe with a write system call, read from the read descriptor with the read system call. Pipes are anonymous. They don't have a name in the file system. Then the question arises, well, if 2 processes want to actually talk to each other using a pipe, what do they do? Well, the trick is they have to be related processes. And by related, I mean that one process creates the pipe, then does a fork, which creates another process. That fork duplicates the file descriptors of the parent in the child. So then you end up with this situation here. We've got a parent that's got 2 descriptors that refer to the pipe, and a child that's got 2 descriptors that likewise refer to the pipe. At that point, the 2 processes can communicate. Now, one of the things you then have to do is close the ends of the pipe that you don't use. Okay, remember I said a pipe is unidirectional. Well, if you want to communicate from the parent to the child, the parent would close its read descriptor for the pipe. Excuse me. The parent would close its read descriptor for the pipe, and the child would close its write descriptor. One thing I should say, I've omitted the error checking from all of these system calls in my examples. You should never do that in a real program, but my slides have a limited space. Okay, closing those descriptors is actually quite important. Okay, closing this descriptor here in the parent, the read descriptor, and the write descriptor in the child, because that's the way that the processes on either end of the pipe can tell whether the process is on the other end of the pipe. So the child can tell that the parent has gone away if all the descriptors here are closed. Then the child will see an end of file on a read. Conversely, the parent can tell that the child's gone away if all of the file descriptors here are closed. Then a write into the pipe will fail with a sig pipe signal or an e pipe error. So the next thing you should do is, having forked, each process should close the end of the pipe that it doesn't need. So there's a more complete example of how you might use a pipe. Okay, the steps there I talked about already. Pipe to create the pipe, fork to create the child process. The 2 processes then share descriptors. Then they each close the descriptors they don't need. Then they do some data transfer. Okay, the parent here is writing a string into the pipe. The child is reading that data from the pipe inside a loop and writing to standard out. And then at the end, the parent closes the file descriptor. At that point, the child's next read will see end of file, a 0 return from the read. Any questions at this point? So if the pipe's empty, a read blocks, and if a pipe is full, a write blocks. There's one other thing to know about pipes. A pipe, if you do a write to a pipe and there are multiple writers to a pipe, then the data can be broken up. So that if you've got, say, 2 processes that both try and write 10,000 bytes to a pipe, the writes will not be written as 10,000 byte pieces. Potentially, they're broken up into pieces of the size pipe buff. Pipe buff is, according to POSIX, at least 512 bytes. In other words, if you write anything less than or equal to 512 bytes, it's guaranteed to be atomic. On every Unix system. On Linux and many other systems, actually, pipe buff is actually 4096. If you write more than those number of bytes, and there's someone else also trying to write to the pipe, then potentially your writes will be broken up into pieces of arbitrary size. That's one of the reasons why I said it doesn't usually make sense to have multiple writers to a pipe. I won't go into it, but the scenario that I showed right back at the beginning there, where you've got a filter writing to a pipe and another filter reading from the pipe. In other words, these are the standard file descriptors 0 and 1. You can accomplish that using the dupe system call. And I've just given a link there of an example of how to do that, to set up exactly that situation shown in that diagram. You can find that there. Pipes have a limited capacity. Before Linux, or up until Linux 2.6.11, it was 4096 bytes. Since then, it's 64K bytes. And even more recently still, you can actually control the capacity of a pipe using an F control system call. I forget which version that was in. It's in the man page. In general, though, you should design your applications not to care about the size of a pipe. If you are doing that, probably there's something wrong with your application design. Pipes are nice. They can only be used between related processes. So one of the other inter-process communication mechanisms that came along soon afterwards was named pipes. A named pipe is just like a pipe, with the difference that it exists as a file in the file system. You create it using the make FIFO function, and then having done that, you can then open the named pipe and read and write just as with a normal pipe, and exactly the same rules apply. There are a few special rules around opening the file or opening the FIFO, because it only makes sense for there to be two processes on the FIFO. Opens are synchronized. In other words, if someone comes along to open a FIFO for reading, that open will block until another process comes along to open it for writing. Okay, and then they're both ready to communicate. There are ways around that. You can open a FIFO reader for reading in non-blocking mode. Sometimes that's useful for a reader to get ready to wait for a writer to come along. Okay, but in general, opens are synchronized. That's pipes. Any questions? Or pipes and named pipes? Okay. There are on Linux or most modern Unix systems two common kinds of IPC that go by the name System 5 IPC and POSIX IPC. They both provide three kinds of communication: shared memory, message queues, and semaphores. I'm only going to talk about the POSIX variations of these IPC methods. The System 5 versions still exist, they're still usable, but their interfaces are rather unpleasant to use in certain respects. So in general, if you're writing new applications, you should use the POSIX methods. So I'm going to start talking about POSIX message queues now. Okay, POSIX message queues, it's message-oriented communication. A writer writes a message, a reader reads a whole message, as I said before. No partial reads, and so on. Messages have priorities. So you write a message into a POSIX queue, the messages are queued up in order of priority. The reader will read the highest priority message first. There's another interesting and somewhat unique feature about POSIX message queues. There's a notification feature whereby you can say, when a new message arrives on this queue that was empty, tell me about it in some way. And there are various ways that you can choose to get informed, and I'll talk about those in a moment. So the API looks pretty much how you'd expect. Just by the way, all of these slides will appear on the net very soon, probably by tomorrow, at a location that I'll show you at the end. And I suppose they'll appear on the LCA side as well. Yeah. Okay, so the API looks sort of like what you'd expect. You've got an open call for opening and creating message queue. It's very much like opening and creating a file. Close, unlink for removing a path name. Send for sending a message to the queue, receive to receive a message, and then there are a few odd looking calls at the end. A few odd looking calls at the end. You can set and get queue attributes using these two functions, and this function here sets up that notification technique that I was talking about. So the way you create a queue, mQOpen, you give it the name of the queue you want to open, flags that control how the open happens, the permissions mode if you're creating a new queue, some attributes for the queue if you want to set some attributes. The name looks like this. It's slash and then some name. It looks like a path name with only one component. That's just the POSIX standard way of doing things. It's visible in a pseudo file system. I'll show you briefly later on about how to actually see the message queues in that file system. And you get back a message queue descriptor, which is the thing that you use for referring to that message queue in the rest of the API. These flags, if you're familiar with the open system call for opening a POSIX message queue, look quite similar to an open system call. Create a queue if it doesn't exist. Create it exclusively. In other words, I want to make sure I'm the one that created it. If there is already a queue by that name that exists, give me an error. Open it for reading, writing, or reading and writing. Open it for non-blocking I/O. The mode sets the permissions on the queue. Attributes sets attributes for the queue. I won't talk too much about attributes, but null will give you some reasonable defaults. So here's how to open a new message queue for writing. mQOpen, here's the name of my queue. Create it exclusively for writing. Permissions 0600, read, write, just for the owner. Default attributes. Open an existing queue for reading. Name of the queue, read only, and I don't need the rest of the arguments. If I don't need the queue anymore, I can unlink the name, just like unlinking a file. Message queues like pipes have a limited capacity. You can control that using the attributes that I talked about before, which I'll briefly mention later on. The two system calls for performing I/O on the queue: receive blocks if there's no messages in the queue, send blocks if the queue is full. O non-block, okay, do non-blocking I/O. So in cases where it would normally block, instead of blocking, give me an error instead. So if I try and read from an empty queue, I'll get an error instead of a blocking. Sending, okay, to send a message, you give it a queue descriptor, a pointer to your message, the length of the message, and the priority for that message. All of that I think is fairly straightforward. 0 is the lowest priority. Anything greater than 0 is a higher priority. So some examples there of sending. Okay, we open a queue as before. Here's our message. Send to the queue. That message, size of the message, and 0 is the priority. Okay, again, I've got some URLs pointing to bigger examples that contain these code samples. Oh, there's a typo there. That should say MQ receive. Here I've written MQ send, that should say MQ receive. Reading the same arguments, a descriptor, a buffer to hold the message, the size of that buffer, and a pointer to an integer which returns the priority of the message that you've read, so you can find out what the priority was. And as the return value of the system call, the number of bytes in the message. So here you say how big the buffer is, and here you find out how many bytes were actually used in the buffer when the system call returned, or when the function returned. Oh, I've done it again. Okay, still the same typo there, but down here I've got the right example. Here, receiving a message from the descriptor, buffer, size of that buffer, which I've got two typos. That should be buffer size there. And then to get the priority here.
What happens if you haven't made your buffer big enough to receive the message?
You'll get an error. Sorry?
Probably e-message.
From memory, I think that's the one, yeah.
And will the message be partially consumed?
No, you just won't. No. There's no partial consumption of messages. I just would mention actually as well that one of the attributes you can set on the queue is the maximum message size. So also if you try and write a message that is too big, potentially you'll get an error as well. Okay, message queue notification is quite a cute trick with message queues. One process can say, I want to get messages, I want to get notifications when a new message appears on an empty queue. Okay, notification only works if the queue was already empty at the time another message arrives. And what you do is you say MQ notify, give it the descriptor, and then a structure that says how you want to be notified. And there are, I won't go into the details, but there is an example in the man page. You can choose how you want to be notified. The two main ways of being notified are, one, send me a signal, or two, start a new thread in my process and give it some information about the message that has just come in. It's a single shot mechanism. Once you've been notified once, if you want to be notified again, you have to do another MQ notify to re-establish the notification mechanism. And you should do it before emptying the queue, because if you empty the queue and then try and re-enable the mechanism, there might be a small window, or there is a small window there where if another message arrives before you've re-enabled notification, the queue isn't empty and you'll never get a notification. I mentioned that there was an attribute structure associated with each message queue. You can set some flags on the message queue. You can set the maximum number of messages in the queue, the maximum size of messages, and you can find out how many messages are currently in the queue. And what I've just shown there is the various functions that get or set that information. I mentioned there was sorry, yes?
So just then to clarify, given that you can find out the length of messages in the queue, you could...
you can find the number of messages in the queue.
Yeah, you could implement a polling style interface. You could say...
Can we actually use poll on the message queue?
Yep. Yeah. I'm going to come back to that a bit later on. This is one of the special things about message queues on POSIX, on Linux. They're actually... Message queue descriptors are actually file descriptors, so you can use poll. That's not a standard thing, but it's a nice feature of the Linux implementation. Okay, I mentioned that there was a file system that could show you your POSIX message queues. You can mount that file system by doing something like this. Make a directory for the mount point. Then you say mount -t, mount the message queue file system, none here, and then the mount point. And then you can list the contents of that directory and see your message queues. So I've got one queue there, mymq, and if you cat that file, you get certain information about the message queue. The number of bytes in the queue, the current notification method in the queue. I forget what 2 is. I think it is notification by thread. So you've got 0, 1, and 2. 0 is no notification. 1 is signals. 2 is thread notification. And if some process has set itself up to be the receiver of notifications for that message queue, you can find out the PID of that process there. Much more detail in the MQ overview page. Any questions or any other questions about POSIX message queues?
The messages of a given priority, are you guaranteed they'll be delivered in order?
At a given priority, they'll be in order. Yeah. That's a good point. I should have actually had that on the slide.
Does anyone actually use message queues? No.
Does anyone actually move? I'm having trouble to think of some concrete examples. There are. I've used them for some applications, but sorry.
Maybe embedded people. The problem is you have to change system-wide variables, so those attributes.
Yeah.
Change them up to a limit, but then you have to system-wide change them to get bigger. So you're limited by tiny little messages and small message queues, so it becomes unusable.
Certainly.
To Unix sockets.
Sorry?
Yeah, more Unix sockets.
Yeah, no, it's certainly in the last organisation where I was working, people were trying to use POSIX message queues for some of their applications. I think I raced past it, or maybe I didn't mention it. Okay, there are per process limits, and as you mentioned, there are system-wide limits as well that control the operation of message queues. Again, the details are in the manual page. Okay, shared memory. The general idea of shared memory is a bunch of processes sharing the same physical pages of memory. When one process updates the contents of that memory, it's immediately visible to any other process on the system. Whoops. So communication is just copying into memory. It's efficient because if you compare it with data transfer, what you're doing is you're copying some data from user space into the kernel, and then you're copying it back out during the read operation. Okay, and copying data in and out of the kernel is a relatively expensive operation. The trick then though is with shared memory you've got to somehow synchronize your access, because synchronization comes for free with data transfer methods. Someone reads, someone writes. With shared memory there's no actual control on the access to the buffer. So this is the situation then that you've got two processes with their page tables, and some of the page table entries in each process point to the same physical pages of memory. There are three types of shared memory that I'll try and race through. Shared anonymous mappings, shared file mappings, and POSIX shared memory. There is a fourth one again which I'm going to leave out, which is System 5 shared memory, because like the rest of the System 5 IPC mechanisms, the interface is not so pretty. Okay, the difference between these three methods, shared anonymous mappings allow related processes to communicate. By related, I mean processes that are related by fork. Shared file mapping can be used between unrelated processes, and they're backed by a file in the traditional file system. POSIX shared memory is for unrelated processes without creating a file in the traditional file system. So you may not want to bother doing I/O on a file, in which case you can use POSIX shared memory instead. All of these system calls, all of these mechanisms make use of the same system call, mmap. Mmap's a rather complex system call. It takes a bit of time to break down. It's got 6 arguments. Those 6 arguments look like this. You've got, let's see what's the best way of, first of all, you want to create a mapping. Dadd says, where do I want that mapping to be in my memory? Normally, you specify that as null, and the system chooses a default value for you to place the mapping. Len says how long I want the mapping to be. Prot says what protections I want on the mapping. Do I want to be able to only read from the memory, or read and write, or perhaps read and write and execute? Flags are various flags that control the operation of the call, and we'll come back to some of those flags later on. FD is a file descriptor which is used for file mappings. Again, we'll come back to that later on. And offset is also used for file mappings. What you get back from the system call is the address where the mapping was actually placed. And even if you do explicitly specify an address here, you may not get back exactly the same address there, because this, at the least the kernel will round it to a page boundary and may simply override your request for some reason. So, once you've made the system call, add looks just like any C pointer. It's just a pointer to the start of the map region. But anytime you make a change to the memory at the location where that pointer points, that change is visible to every other process that shares the mapping. So I said there were 3 types of mappings. Here's the first one, a shared anonymous mapping. It works between related processes, and related is related in the same sense as pipe, as a pipe. You don't need a file descriptor and an offset because we're not making use of files. So those 2 items are specified as -1 and 0. And what you do is you say, I want to create a mapping, and then I do a fork. And the consequence of a fork is all the page table entries in the child process are duplicates of the parent's page table entries, pointing to the same physical pages of memory for that mapping. Okay, in this case here I've said, okay, whatever length of the mapping I want to be able to read and write the contents of that memory. Shared says, okay, I'm going to share this mapping with other processes. Anonymous says there is no file connected with this mapping. So you get a 0 initialized block of that size, and the parent and the child after that fork share that memory at address for length bytes. Probably I've said everything I need to say about this. I did have a few more slides just to break this down. Are there any questions about what that system call, or those 2 system calls together do? Okay, a shared file mapping. The idea is you open a file, you map the contents of that file into memory, and then anytime you make changes to the memory in that region, not only are they shared with other processes, they're also automatically updated to the file. Okay, so the file provides a kind of persistent storage backing up the shared memory. So shared file mappings, there's 2 steps, open plus mmap. With a shared anonymous mapping, the mapping was initialized to 0, but when you open a file and map it, the contents of the memory are initialized from the file. And as I said, any changes you make to the file, to the memory, are automatically carried through to the file, and all the processes that map the mapping share those updates in the memory, and their updates are propagated through to the file. So that's showing the situation there where you've got multiple processes. They're sharing the same map pages. The I/O to the file is managed by the kernel. Okay, processes by and large, don't need to do anything to make this happen. There is a system called msync, which says make sure that the current contents of memory are forced out to disk. If you want to ensure that that's actually happened recently. So, create a shared mapping, open the file that you want to map, open it for reading and writing in this case because I want to update the mapping. Map null, let the system choose an address, size of the mapping that I want to map from that file. I want to map it for reading and writing. I want to share my updates with other processes. Here's the file descriptor of the file that I want to map. And 0 there is the offset. It says from what point in the file do I want to map. So 0 here says I want to map from the start of the file. But you could specify a mapping that started at some other point in the file as well. It'll need to be page aligned within the file. And at some point you probably don't need the file descriptor anymore and you can just throw it away. Again, I think I've walked through that already. And again, as a result of the system call, you get the address at which the mapping was placed in memory. Any questions about shared memory mappings? Or shared file mappings, I should say.
What file systems support MC?
Sorry?
What file systems support it?
I think it's rather a question of which ones don't support it. I think most file systems do support it. I can't offhand, I can't think of any common file system that doesn't. Yeah, so the file, a file system does have to support it, but
It mounts under dev SHM, but on different Unixes it can be in slightly different places.
Yeah.
The other thing to note is you should write to that file the full length that you want to write to, because often if dev SHM fills up, you won't know until you actually try to write to it, which might be too late.
I think you don't mean dev SHM, I think you mean...
No, not to the whole directory, to your file.
Yes.
So if you say open a meg,
yeah,
and it's not going to be there, you won't know until you finally get there, and then you'll get a nasty session.
Right, depending on your overcommit policy. Yeah. Okay, POSIX shared memory is the third variation there. The difference between the two previous ones, it's for sharing memory between unrelated processes, but with the difference that you don't need to create a file and do file I/O. Okay, you may not want. You may not need this file backup, and you don't want the kernel to go through the extra work of syncing all of your updates to the file. But you do want unrelated processes to communicate. Okay, in that case, you can use POSIX shared memory to achieve that scenario. Okay. The API looks a little bit familiar from POSIX semaphores. Shared memory open, okay, open or create the shared memory object. mmap to map the object into memory. If you don't need the object anymore, unlink it with shared memory unlink. Then there are some other system calls that are also useful with POSIX shared memory. fstat allows you to find out the size of a shared memory object. Okay, fstat is the general purpose system call for getting the attributes of a file. Well, you can apply fstat to the file descriptor that you get back from shared memory open to find out the size of an existing object. ftruncate, again, you can apply it to this file descriptor to change the size of the mapping. And you can change the ownership and the permissions on a shared memory object as well. So, opening a shared memory object, you say shared memory open, name of the object, flags that control the open, and the permissions that are going to be placed on the object. So that'll open an existing object, or open and create a new object. The name looks just like the POSIX semaphores. You say slash some name. You can see that name in a dedicated temp file system at /dev/shm. you get back a file descriptor that you use in the rest of the API. Okay, the flags, most of them look pretty familiar. Create the object if it doesn't exist, make it an exclusive create. Do I want to have this mapping for read-only access or for reading and writing? And if it's an existing object, I can truncate it to 0 length. And I can set the permissions. Whoops. Okay. Unlike the open system call, this argument is always required. But if you're not creating a new object, you must specify mode as 0, but you can't omit it. So, an example there, creating and mapping a new shared memory object, size bytes. Okay, I say shared mem open, give my path name. I want to create it exclusively for reading and writing, permissions for reading and writing by the owner only. I change the size of the object because to begin with a new object has 0 size, so I say f truncate that file descriptor to my desired size, and then I say map that object, add an address chosen by the system, here's its size again, here is the permissions I want on that memory. I want to map it shared so other people, other processes can see my updates. Here's the file descriptor I want to map, and map from offset 0 in that shared memory object. And I get back the address where the mapping is placed. Again, I think I've run through all of those bits and pieces, haven't I? Any questions about that? Okay, now if you've got an existing shared memory object, things look slightly different. You say open it, there's the path name, I'm going to read and write that object, 0 for the mode because I'm not creating the object, so I have to specify 0 there as the permissions. Then I need to find out how big that object is because someone else has already created it and sized it. So I make an fstat call which passes one of these stat structures as a second argument, and as a result I get back the size of that object. And I use that in my mmap call to specify how big my mapping is. And then it looks very much the same as before. Okay, the thing is then, you've got two processes that share memory. How do they synchronize their access so that one process doesn't try and do an update at the same time as another process, or one process doesn't try and read data from the shared memory at the same time as another process is in the middle of updating that data? So you need a synchronization technique. There are two commonly used synchronization techniques for synchronizing between processes on Linux or on Unix systems generally. Semaphores, which are the technique usually used with shared memory, and file locks, which are the technique usually used for synchronizing access to files. And what I want to talk about now is POSIX semaphores. Okay, a POSIX semaphore is just an integer that is held inside the kernel, and it has a special property that if you try and update the integer in a way that would push its value below 0, then the kernel just blocks the call until such a time as the operation can be done without pushing the semaphore's value below 0. So, for example, if the semaphore's value is currently 0 and someone tries to decrease that to -1, the call will block until someone else comes along and adds 1 to the value of the semaphore. Then your operation will proceed and you can decrease the semaphore again to 0. Okay, two fundamental operations for a POSIX semaphore. Sem post, increment the semaphore by 1. Sem wait, decrement the semaphore by 1. Sorry about that. These typos will be fixed by the time the slides go up. Okay. So post is increase, wait is decrease. And the wait operation is the one that can block. Okay. A semaphore is just an abstract thing. It just represents whatever shared resource you care to associate with it. It could be a bunch of printers, it could be a bunch of buffers in memory that are being shared between processes. Your semaphore value basically represents the number of available resources of that type that you're sharing. So a semaphore can have an arbitrary or an initial value that is some arbitrary number. If you're sharing 5 buffers between processes, your semaphore's initial value might be 5, and then you decrease it as those buffers are allocated out to processes. And if they're all allocated out, the semaphore's value becomes 0 and no one else can allocate a buffer until one of the processes releases the semaphore, increases the value of the semaphore. A very common way of using semaphores, though, is just 0 and 1. In other words, a binary semaphore. In other words, there's a single resource and the semaphore only has the values 0 and 1. The example that is relevant there for us is shared memory. Normally, you only want one process to update the shared memory at a time. So the semaphore's value is either 0 or 1. There's two types of POSIX semaphores. There's what are called unnamed semaphores or anonymous semaphores. The way to share those between processes is to put them into the same piece of shared memory. So you can do something like creating a shared memory object and embedding a semaphore inside that shared memory object. The other flavour is named semaphores, and these exist independently of anything else. They're objects that you create and manipulate and then destroy or unlink. Then you've got a bunch of operations for performing on these semaphores. Okay, for unnamed semaphores, these are the operations you can perform. Seminit says, I want to initialize a semaphore to a given value. And you specify as well a thing called the pshared parameter. And the pshared parameter says, what kind of sharing do I want for the semaphore? And you can either say, well, this semaphore is going to be shared between threads, so I specify 0 here, or it's going to be non-zero, which means I share between processes. And depending on what you're wanting to do there, this is a hint to the kernel, which may help it optimize the use of the semaphore. Okay, depending on whether you're sharing between processes or threads. Sem post, add 1 to the value of the semaphore. Sem wait, decrease 1 from the value of the semaphore. Sem destroy, I've finished with the semaphore, free all the resources associated with the semaphore so that they can be reused by the system. So an example of how you might use semaphores, if you tried to use shared memory as a kind of pipe, you could have a reader and writer and implement this sort of scenario where I've got a writer here that is reading data from somewhere else, writing into the shared memory, and another process which is reading from the shared memory, copying that data out and perhaps writing it. Another typo. Should be saying copy the data block from shared memory to standard out. That'll be fixed as well. Okay, now you can. The point here is that you want your two processes to have synchronized access to the memory so that this process here doesn't try and read at the same time as this process is trying to write. That's one thing you want to achieve. You could do that with a single semaphore, but not only that, you want to enforce lockstep access. In other words, first of all, the writer has a turn, then the reader, then the writer, then the reader, then the writer, then the reader. Otherwise, you might have a situation where a writer writes two buffers into memory, one on top of the other, before the reader has had a chance to read one of those buffers. Okay, and the way to do that then is with two semaphores, which I've called the writer semaphore and the reader semaphore. Okay, you set things up so that initially the writer semaphore is available, it has the value 1, and the writer says, okay, I'm going to wait till the semaphore value is 1. Then when it is 1, I'll decrease it and update the shared memory. And then I'll tell the reader that its semaphore is now available. Okay, its semaphore, we assume to begin with, has the value 0. And the reader is going through a similar sort of loop. It says, I'm going to wait for my semaphore to be available, then I'll read the data from the shared memory, and then I'll tell the writer that it can have a turn. So you've constantly got the semaphores flipping backwards and forwards to allow the two processes to alternate their access. Okay, I just will look at a little bit of code that does this. So here's a buffer, or here's the data structure that I'm going to use to structure a piece of shared memory to allow this sort of data transfer. The buffer has the two semaphores embedded inside it, the writer semaphore and the reader semaphore. And then there is the data buffer itself and a counter that says how much data is actually being used inside that buffer. Then my writer process looks like this. I create a block of POSIX shared memory in the usual way, with shared memory open, size it with ftruncate, map it into memory, and then inside that block of memory I initialize the two semaphores. I initialize the reader semaphore. Okay, they're both process shared. The reader semaphore gets the value 0. The writer semaphore gets the value 1. And going back to that diagram, that means the writer is going to be the first one to get a turn, because when the reader tries to wait for its semaphore, it'll block. Okay, and then we just go into a loop where the writer is reading some bytes from standard input. It waits for its semaphore to become available, reads some data from standard input, puts it into the buffer part of the shared memory, updates the count inside that. Okay, going back here, and we've got a count and a buffer. Updates the count and the buffer, and then says to the reader, there's something there for you to do now, and it posts its semaphore. And it just goes round and round that loop. At the end, it's going to break out of the loop when there is no more data to read. Okay, so when the read here returns end of file, and at that point it'll just do one more wait for the reader to finish its last access to the memory. And then the writer can now do all the cleanups required, like destroying shared memory and semaphores. The reader, okay, it's a similar sort of thing, but in reverse. It opens an existing shared memory object. It opens an existing shared memory object, maps it into memory, and then goes into a loop where it waits for its semaphore, and then it writes data from the buffer, count bytes. Oh, okay, that's a little typo there as well, sorry. I was trying to trim out all the error handling code, and I just missed trimming out that piece. And then it tells the writer, it's now your turn. And this is the loop termination piece here, which says, well, if the buffer that I've received just now has 0 length, that means the writer had nothing more for me. So I'll just break out of the loop, and then I'll tell the writer, I'm finished now. And that's synchronized with that last wait that was performed by the writer, so that the writer can know the reader is finished. Any questions?
Is there any protection against error post?
Semaphores are amusingly being called the go-tos of synchronized programming. No. Anybody can manipulate, or anybody who's got permissions on the object can manipulate the semaphore in any direction. So it's different, for example, from a mutex, where when you acquire a mutex, you own the mutex, and only you can release the mutex.
Latency when compared to a pipe? Latency compared to a pipe?
Latency when compared to a pipe. I try not to make any statements about performance. And the reason I'm not being glib. It's like every example depends on your application. The only sensible thing to do is to benchmark your particular application. To say, semaphores are faster than some other mechanism, or shared memory is faster than pipes. It all depends on your use case. Having said that, mutexes are pretty fast. If you're talking about threaded programming, at least. That's unnamed semaphores. Named semaphores, again, this story starts to look pretty familiar here. How long do I have, by the way?
I think we've got another IPC.
Great. Okay. Named semaphores looks fairly similar to the POSIX APIs we've seen already. You've got an open call that says open and possibly create me an object. Unlinked says get rid of the path name for that object. So you say semopen, the name of the object you want to open, flags that control the call, permissions for the object you're creating, and here you can specify the initial value of the new semaphore you're creating. Those last two arguments are only needed if you are creating a new semaphore. Again, the name has this form slash and some name. Again, you can see the semaphores, the named semaphores you've created in this tempfs at /dev/shm. You get back a pointer to a semt, which is just a reference to the semaphore, and you use that in the rest of the API. So the flags that you can specify there, create, okay, I want to create the object if it doesn't exist, create it exclusively. I want to make sure I'm the one that created it. And as I said, the other two arguments here are only needed if you're creating a new semaphore. Oh. And that's as much as I have to say about semaphores. Any questions? Maybe we are going to have time to get to file locks and other pieces. Okay, so next IPC mechanism, sockets. Sockets really is a very big topic, so I'm not going to try and go into the details of the APIs, but just to give you some very high-level picture of how sockets, or how the API pieces work together. And then mention some notable features about sockets as a method of inter-process communication. The very first, or I don't know if it was, well, the very first, I think, published document about sockets that made its way to the outside world had this wonderful sentence: a socket is an endpoint of communication, which completely baffled me when I read it. Because the next sentence should have said, you need two of them. Okay, you create two sockets and then you join them together, or you send messages between them. Sockets are unlike pipes, for example. They're bidirectional. With a socket, you can both read and write data on the socket. You create them with a socket system call, and you specify three things in that system call, and I'll talk about two of them in a moment. A domain and a type. You can also specify a protocol, but for most, or for all the cases I'm going to talk about, the protocol is always 0. But there are some cases where we can specify a non-zero protocol usefully. You get back a file descriptor which refers to the socket. So it looks like a similar sort of thing to what you get from a pipe in terms of a file descriptor. So I said there, sockets have a domain and a type. Well, a domain is specifies essentially the range of communication for that socket. Is it communication on a single host, or is it communication across a network? That's the thing that's specified by a domain. And coupled with that then is the method of how you're going to identify this socket. Okay. Either you're going to have a method that identifies the socket on a single host, or it identifies the socket in the context of a network. There are 3 common domains that are used by almost all, or they're available on all Unix systems and most other systems nowadays as well. The Unix, I'll rephrase that. These 2 are available on most systems. This one is available only on Unix systems normally. Unix domain is for communication on a single host. The address of a Unix domain socket is just a path name. Okay, so that's how applications identify each other's sockets. IP4 domain, AFINet, is for communication over an IPv4 network. The address that's used for identifying sockets is an IPv4 host address, 32 bits, and a port number. The port number there just distinguishes, okay, you've got 20 different applications on the same host. You need a way of distinguishing those various applications. Well, they're connected to different port numbers. Okay, and so when I want to connect to a particular application on an IPv4 host, I specify the IP address of that machine and the port number where I know that application is connected. IPv6, it's the same idea but across IPv6 networks. 128-bit address this time plus a port number. Now, the other thing that you've got when you create a socket using the socket system call is the type. The type tells you about the semantics of the communication. And you've got 2 main types available. You've got stream sockets, which are byte stream, and you've got datagram sockets, which are message oriented. Some systems, including Linux, provide other socket types. One socket type that you find on Linux with Unix domain sockets is sequential packet socket. And a sequential packet socket, as I'll mention a bit later on, is sort of like a cross between these 2. It falls somewhere in between. So a stream socket, it's a byte stream. It's a byte stream, so therefore necessarily connection oriented. You've got 2, it's like a telephone call. You have 2 sockets that are connected to each other and they're just streaming bytes to one another. Readers can read any arbitrary number of bytes, writers can write any arbitrary number of bytes. There's no connection between what the reader must read versus what the writer has written.
Use duplets.
Yeah, so you can do things in both directions. There's 2 channels on a socket. Yeah. A stream socket is reliable. What that means is either the data arrives intact or it doesn't arrive at all. In other words, things just broke down completely. Intact means it arrived in order and unduplicated. In the internet domain, this is accomplished over the TCP protocol. Oops, just too slow. Okay, then you've got datagram sockets. It's a message-oriented type of communication. It's connectionless. It's like the postal system. You can fire out a message using your datagram socket. You can fire out a message to any other socket, any other datagram socket that, whose address you know. It's unreliable. What that means is messages may be duplicated. They may arrive out of order, or they might not arrive at all. Your application level logic has to handle that possibility. In the internet domain, datagram sockets are implemented using the UDP protocol. This third type of socket that I mentioned, it's not so commonly used because not all systems have it, but a sequential packet socket is a bit like a mixture of those two socket types that I've talked about just already. It's message-oriented communication, so whole messages are read and written, but it's connection-oriented and reliable. Okay, and on Linux, that's only available on the Unix domain. Well, I'll rephrase that. On Linux, you have sequential packets in the Unix domain. You do have them also in the Internet domain if you're using something called the SCTP transport protocol, okay, which is an alternative to UDP and TCP. But it's not so widely available as the traditional protocols.
Yeah, just on that one.
Yeah.
Is it commonly used?
Sequential packet?
Yeah.
No, because it's not so widely available. But if you're writing just a Linux-specific application, there's absolutely no reason why you can't use a Unix domain sequential packet socket. Is that visible down the back? Because I've got also this version in two pieces. Okay, this is just, the idea is just to show you here how all the system calls that are working with stream sockets are used together. So I've just to make it a bit more visible, I've cut the diagram into two pieces, and so the top half is this piece here. To do stream-oriented communication with sockets, you normally have what are called an active and a passive socket. An active socket is the one who starts up the connection, if you like. The passive socket is the one that waits for a connection. Okay, so if you're going to wait for a connection, there's various things you have to do. First, you have to create your socket. Bind says, give my socket an address so that other people know where I am. Listen says, well, I may have multiple clients that are going to connect to me, and I may not be able to may not be able to respond to them all immediately to their connection requests. I'm going to set up a queue of length n to allow those incoming connection requests to queue up and wait until I've got a chance to deal with them. And then accept says I want to accept a connection. So commonly you'd have an application that performs an accept in a loop if it wants to deal with multiple clients. It will do an accept to accept one connection, do all the I/O on that connection perhaps, and then go around the loop again to accept the next connection. Accept blocks until an active socket comes along. Okay, an active client says, I'm going to create a socket, and then I'm going to connect to the address that was specified here by the bind. And at that point, the accept unblocks, and the two processes can then communicate using traditional system calls, read and write backwards and forwards. When they've done, they can close their ends of the socket. That's the same information that I've just gone through in summary form. Any questions? Okay, for I/O you've got read and write and close. There are also there are a number of socket-specific system calls, but two that you might use with stream sockets are send and receive. They're just like write and read, except they've got an extra flags argument that allows you to add some socket-specific behavior to the I/O operation. Any questions about stream sockets?
When you're using send and receive, can you mix the types?
When you say mix the types?
So can you use write and send at the same?
No problem. Yeah. It wouldn't be common to do so, but there's absolutely no reason why you can't. Okay, datagram sockets are a whole lot simpler in a way because there's no connection involved. All that happens is that two processes create their sockets. At least one of them has to bind to an address. and then they can send data to and from each other using two special socket system calls, receive from and send to. Send to says, I want to send data, and you specify an address. Receive from says, okay, give me some data that's being sent to me. Receive from has the capacity to also, as well as receiving the data, to receive the sender's address. So after a receive from, you can typically turn straight around and do a send to back to the address that you've just discovered. And again, when the two processes are finished, they can close their sockets. Any questions? Okay, again, the same information summarized. So I just want to mention a few noteworthy points about sockets, reasons why you might choose to use sockets for particular purposes. I said that datagram sockets are not reliable. Well, in the Unix domain they are, because it's all happening on the same host system. There's no problems with networks to worry about. So Unix domain sockets, at least on Linux, and I think every Unix system are reliable. Unix domain datagram sockets.
So is there any point then to the sequence packets on a Unix socket? You know what, if you know what I mean? If they're reliable, that's what the sequence packet gives you. And ordering. Yeah.
I think in theory there is no reason.
So from portability,
or in practice there is no reason. Yeah, there's a portability. Yeah.
You might want to stick to.
You might want to stick to datagram sockets. Yes. I'm not sure. Certainly in the early Unix systems that I came across, there was never any stated guarantee about Unix domain sockets, datagram sockets being reliable. I never thought back then to actually test that. And now those systems, I don't have them anymore. It's a long time ago. But you know, every modern system that I've been able to test, Unix domain sockets are reliable. Unix domain datagram sockets are reliable. Another interesting thing you can do with Unix domain sockets, which is quite special, is you can pass file descriptors across Unix domain socket. And what I mean by this is you've got two processes. One of them opens a file and then creates a connection to another process using a socket, and then uses a special system call, a special socket-related system call, send message, to actually pass the file descriptor that is just opened to the other process. So it's a way of, in effect, passing access rights to a file object from one process to another, and that actually finds a lot of uses in different places.
That's for passing event files.
Sorry?
Not passing event files.
For all sorts of file descriptors. I think, among others, for instance, Systemd uses this technique as well for hanging its pieces together. I forget the details. Network. Sorry, question?
When you're passing file descriptors between processes, would permissions prevent that?
No, this is a short answer. First of all, it's all under application control. So, you know, the two processes have created a socket. One assumes that they've decided they want to pass the file descriptor between them. So, you know, the application is not going to pass a file descriptor to some other random process. These are processes that are designed to work together. So there's no need for access control as such. The application's already enforced that. Yeah? Yeah. So, internet domain sockets are the only method of IPC over a network. So that's the reason why you might want to use internet domain sockets. UDP sockets have the characteristic that you can broadcast a datagram to multiple receivers, or multicast a datagram to selected receivers. One other system call that I didn't mention so far, but which again might be useful, socket pair is a system call which creates essentially a bidirectional pipe. Okay, it looks just like a pipe call. You give it an array of 2 file descriptors. It gives you back a reading, it gives you back 2 ends of a socket pair that you can then fork, and 2 processes can communicate in a bidirectional fashion using that socket pair. $12.20, is it?
Yeah, it's 12:20. We have 5, 10, and 1 minute signs.
Okay.
We'll have 5 minutes question time at the end too.
Okay, so
you've got another 20 minutes. And then
I've got another 20 minutes.
Time.
I just want to have a little think about whether I'm going to try and squeeze in anything more, other than a few discriminating factors between IPC mechanisms. Now I think I'll just see how I go with these pieces. Okay, there are some other criteria that you might use for selecting between IPC mechanisms. And I just want to look at some of those. There are some obvious things: consistency with your application design, functionality that is consistent with what you want, but there are other criteria as well. First of all, every IPC object has an identifier, which is the thing that identifies, how do you find the IPC object, and a handle, which is the thing that you use to refer to the object when you are actually working with it. So if we took that analogy back to files, the ID is the path name of a file, a handle is the file descriptor. Okay, there's an analogy in most cases with each kind of IPC object as well. So what I've got there is, for various IPC methods, a table that says, well, how are objects identified and what kind of handle do you actually use to refer to them when you're working with them inside a program. So pipes, for example, have no name. FIFOs have a file system path name. Unix domain sockets have a file system path name. Internet domain sockets have an address and a port number, and so on and so on. When you're working with those objects inside a program, well, many objects are accessed via a file descriptor. There are some other possible handles there. I talked already about a message queue descriptor, a sem underscore t star for semaphores. I haven't talked about System 5 IPC, but they have their own special identifiers, which are weird and wonderful. One of the relevances of all of that is the things that use file descriptors can be multiplexed. So any of those techniques there that uses a file descriptor for data communication, so pipes, FIFOs, sockets, where are we? Message queues. Okay, message queues. A message queue descriptor really is a file descriptor. Any of those techniques can be used with poll, select, and epoll, so that you can monitor multiple descriptors at the same time to see if I/O is possible on any of them. Okay, you often have a situation where you've got a network server, for instance, that is handling multiple clients at the same time. It wants to find out whether there is something to read from all of those clients. Well, it can monitor all of those clients at once using one of these mechanisms. Yeah, I'm sorry, I don't have time to go into that. I just want to let you know that this does exist. It's a mechanism for monitoring multiple file descriptors, saying, is it possible to do I/O now on any of these file descriptors? I think there are now examples in all of those manual pages, so you should be able to piece it together. It's just worth knowing they exist. So you can use these mechanisms with all of those IPC mechanisms, and this is one more good reason why people avoid System 5 message queues, because they don't use file descriptors and you can't use these techniques. Another discriminating factor for why you might choose a particular IPC mechanism is how is the access to the mechanism controlled? Well, there are various possibilities. It could be based on user and group IDs and a permissions mask. It could be based on whether the processes are related via fork, or it could be something else. It could be something determined by the application, for instance, which is what happens with internet domain sockets. So, again, I've tabulated there for various IPC mechanisms what the mechanism is that defines accessibility. For a lot of mechanisms, it is a permissions mask, in other words, a user and group ID that are associated with the object, and read-write permissions for 3 different classes of user. Some objects like pipes, it's related processes. And then, where are we? Do I have sockets on this table? Yeah. For sockets, any process can access the socket, but the applications determine who they're going to communicate with.
And you can also send on this magic send message, receive message, and get the actual user ID, group ID.
Yeah, there is. Yeah.
So you can get a finer grained access control.
You can, and you can lie about it. You can spoof if you have sufficient privileges. So then you have sufficient privileges. Yeah. Sorry, I need to pause there. That's for Unix domain sockets. Yeah. So where I was talking about internet domain. Yeah. Yeah. Okay. For semaphores, for unnamed semaphores, it depends on what the permissions are for the underlying memory, how the memory is being shared. Another discriminating factor for how you might choose an IPC is based on its persistence. Okay, how long does the IPC object live? Well, it could just have process persistence. What that means is the object only exists as long as at least one process is connected to it. It could have kernel persistence, which means it lives as long as this boot of the kernel lives. When the system reboots, then the IPC object is gone. Or it could have file system persistence, which means that actually it might live even across a reboot. So, for instance, some of these IPC mechanisms only have process persistence. Pipes and FIFOs, the data in the pipe or a FIFO only exists as long as at least one process is connected to that FIFO. Okay, that's notable, by the way. A FIFO has a name in a file system, but that doesn't mean that its data is persistent if no process actually has the FIFO open. Various other mechanisms have process persistence. POSIX message queues and semaphores and POSIX shared memory have kernel persistence. So what that means is I've got 10 minutes, I can create a POSIX message queue, put some messages on it, and then disconnect from the POSIX message queue. My process can terminate. Those messages will still stay there until some other process comes along, opens the message queue for reading, and reads the messages. But they'll disappear if the system reboots. There's one type of object which you might loosely say has file system persistence, which is memory mapped files. Okay, if you map a file into memory as a shared file mapping, then the updates that you make to that file that you make to the memory are pushed through to the file. Well, obviously, if they're pushed through the file survives a reboot. Okay, you could then remap that file after the system restarts. Any questions on those discriminating factors? And I think I will stop there and take questions in case there are any more.
Just on the last one with the memory map file, how do we make sure that the file is consistent with the memory? So what's the mechanism? Does the kernel block until the file is consistent?
Essentially, it's the kernel's paging mechanism, which just keeps things in sync. So the mapped file is essentially the paging store for that memory, which means that who knows when it precisely updates, but you can control that with this msync system call.
Does that apply if the process exits unexpectedly? Are the pages updated if the process is killed?
I always do an msync. It's never been quite clear to me, reading documentation and standards, what is guaranteed. But if you do an msync, you're supposed to have a guarantee.
It should still be in the page cache, but you want to be guaranteed that the system will crash.
Yeah, just msync.
I mean, if you're using it for IPC, you probably don't care. And it's more of an issue that you actually want to clean up. And so to me, the systems process is much stronger because you want to help things actually clean up if you crash or whatever.
Yeah,
it's a whole other angle, is that you don't want things that are system-wide. So if the two sides crash independently, actually things get cleaned up. You don't want system-wide things just left there.
Yeah, it all depends on your use case. But yeah, you don't necessarily want to have this sort of persistence.
The last little bit of questions, so that I'm getting from there, they're not hearing the questions very well on the AV. Can I just get people to put up their hands and I'll run the mic over? So who has questions? Okay.
So what techniques do you use to ensure that there's a single instance of an application running, like say Firefox, for instance?
Well, that's kind of a separate question. The point is, you want to create you need to have some proxy to ensure that in a way. So, some object that you create that only one process can create. The traditional way of doing that on Unix systems is to create a file and place an exclusive lock on it. But you could create one of these persistent IPC objects, and if there's already one there, you could use that as your proxy for deciding the process doesn't exist. Doing things with a file has a few virtues because people do things like writing a process ID into the file to so that if someone then comes along and reads the file, they can say, well, actually it's locked at the moment by this process. So I know whether, and then I can know actually, well, maybe that process died. The PID was this, but there's no process with that PID on there. This lock file is actually invalid. I'll just delete it. That's the traditional Unix way of doing things.
This may be a little bit easy, but a while back I did a little bit of work with Ubuntu 10.4, and I tried to see if the socket was writable using select this to do with socket to socket.
Yeah.
And I got a send message called failure saying bad descriptor error.
Okay, so it's a mistake. I think what you're talking about is a mistake that people often make with the select and poll system calls. What those system calls say, I think I actually said it myself, they tell you whether a file descriptor is readable or writable. Well, what is really meant by readable or writable is a read call could be performed without blocking, or a write call could be performed without blocking. Now, that might mean either that the data can be written, or the write call is going to fail straight away for some reason. And that's what select and poll are telling you. Either the write will succeed immediately, or it's going to fail because the descriptor isn't writable for some reason.
Do you think there's a possibility where we can use a cmessage len to the macro to adjust something in the selector?
To do what?
Using the CMSGLAN macro.
Yeah, but in order to do what?
To fix the problem with maybe the language of the selector.
I don't think so. It's a little hard for me to say without knowing more about what you're doing, but I don't think so. Really, applications, just if they're using select and poll, need to be built around the possibility that, you know, readiness means, all it says is the system call won't block. Okay, which doesn't mean data will be transferred. It means either data will be transferred or the system call has an error condition.
Sorry, it's more of a statement than a question, but I'd like to point out that for the internet domain sockets, I'm kind of flying the flag for the IPv6 guys. When you're writing the server side, you can use the address family unspec to support either IPv4 or IPv6, so that your client can connect using AFINet or AFINet 6. Yeah. That's my IPv6 plug.
Like I said, it's a big topic. Any other questions? Thank you very much. Oh.
We have one very latecomer question here. No, too late now.
So how do these compare to something like dbus?
dbus is really a much higher level sort of thing. It's a much higher level of abstraction where I'm no dbus expert, but the point is it's a high level mechanism for processes to discover each other and set up parameters for how they're going to do things. But dbus, for instance, has very poor bandwidth and responsiveness. So you might use dbus to synchronize some stuff between your desktop applications, but if you want to pass vast volumes of data quickly, you wouldn't use dbus for that. Some
control and structured messaging.
As long as there aren't a lot of messages. It's a very good abstraction where you've got a bunch of unrelated processes, they want to discover each other.
Okay, any other final questions? No? Okay, well, can you all join me in thanking Michael for a fantastic talk? Thank you very much, and we hope to see you again.